But you do need to start thinking about, that final a little bit. I'm not saying, that Britt needs to go and study for her final exam in A&P for 2 hours tonight. But I am saying, right, that what I do for the finals, I pretty much just pull off of your old exams, right? You can review, right, your old exams on Moodle, right? You can look at them. And so you can kind of read through those, say, hey, what did I get right? What did I get wrong? I'll tell you right now, I don't know if I mentioned this, but the final is all multiple choice, right? Don't clap yet, because some of you do some interesting things when it comes to multiple choice, right? I feel like multiple choice for me sometimes is a trap, right? Or a lot of you like to overthink it, right? Please note too, what I could also do is, something that was like an essay question, right? I can turn that into multiple choice, questions. So I'm not going to take this as an opportunity to introduce new topics at all, right? Everything in that case will be the same. But I'm also saying don't just look over the matching and don't just look over the multiple choice from previous exams. Look over the short essay questions. Look over those like 2-point definition. Look over those fill in the blank. Oh, I might have some fill in the blank also, right? But fill in the blank multiple choice, I mean, come on, it's not, right? I think it's still a pretty sweet deal. Most people have it done in under an hour. All right. How many questions? Somewhere in the 70 to 80 range, right? You think about it, for the most part, my multiple choice stay at 2 points a question. If I do some fill in the blank, right, they might be like 1 point. So yeah, I'd say somewhere in the 70 to 80. I mean, I'll look over it. I'll give you an exact number here at some point soon if you really want it, but 70 to 80. Yeah. Do you need to come, huh? That is an excellent question. I don't know. I have to think about that. Yeah. I think if I wrote it down right, it's November 24th. Because finals start the 19th, yeah. Well, I mean, I guess I'm open for negotiation. I might let you guys take that at home. With their cameras on, though. Yeah. What? So what do we do like the end of the exam or there's not that much time, right? I have set up wait, let's see, I'm looking at the right thing. November. What day did I say your A&P exam is? No, the last exam. It's the 11th. Yeah, so I just have right now I plan on giving you the Friday the 13th off. And then using the last 2 days of class as a review opportunity. Or do you want to hear what or is? No, I don't think you do. Right. So that's what we're gonna go with, right? Yeah. So that way we're not like, and this has happened before. I mean, I've had semesters where, you take your last exam on Monday, reading days Wednesday, and your finals Thursday. And so I purposely kind of set it up so that there's some time in between. I'm going to make the review stuff optional. There'll probably be some extra credit stuff that's added into those review days if you actually show up. But at that point, I will probably not require you to show up anymore. It'll just kind of be dealer's choice. But, right, the extra credit will be if you show up Zoom doesn't count unless you're Mackenzie, you know, who's been Zooming all semester, right? So, you know, that'll be what it'd be. But so essentially, after you take your 4th exam in here, class becomes optional. But I'll be here to review and answer questions. Okay. Cool. With that being said, speaking of review, let's talk about how we generate an action potential, right? And I want you to kind of go back to the beginning, starting with that glorious, wonderful resting neuron. How do we generate an action potential? Getting tired and old. All right. Generate an action. Start with a resting. Uh, membrane potential is negative 70 millivolts. Right? It's a neuron that's just kind of, it's there, it's not being simulated, it's not receiving any signals, it's at negative 70 millivolts. Okay, perfect. So that's a good starting point. So why is it at negative 70 millivolts, Britt? Okay. Okay, so you have a sodium-potassium pump, pumping sodium out, pumping potassium in. I think you're then also referring to there's a little bit of a membrane leak, and so sodium's trying to get back in, although it can't get back in at the rate that it's getting pumped out. And then the opposite is true for potassium, right? Potassium's trying to get out, right? But we're pumping it in faster than it's getting out, all right? So cool. So those are two important things, right? The sodium-potassium pump and membrane leak. What else? Virginia, can you help me out? So those are positively charged ions that I'm talking about. So why do I have a negative charge on my neuron? What in it makes it negative? Do you have that in your notes? No? Okay. Okay, who can help Virginia out a little bit? Right, so specifically phosphate and sulfate, negatively charged ions. Remember, when you're negatively charged inside of a cell, you're essentially trapped, right? So if we want to change the charge of the cell, right, you know, some of you might think, well, let's just get rid of the negatively charged ions. You can't do that. They're trapped on the inside, right? So it's going to be the movement of positively charged ions in or out that are going to affect the membrane potential, aka the charge of that cell. Okay, so that's good, right? So we have our sodium-potassium pump, we have our membrane leak, right? We have our negatively charged ions that are on the inside. What is the first thing then that happens as part of a depolarization event? Andy? Okay. So we have a neurotransmitter that's released. What does it do? We'll save that one for Paul, what does the neurotransmitter? It opens something. What does it open? Okay, so, well, not exactly. It opens a channel. All right, so it opens a channel. Maddie, what type of channel does it open? Thank you, Maddie. I agree. Okay, so it's an ion channel. What type of ion channel? Right, who can help Maddie out? Or maybe you can answer. We have two types of ion channels. Okay, gated. Okay, what type of gated? Well, sodium moves through this one channel, but this is even kind of more general. Sebastian, were you waving at me, or did you know? So the channel that we're specifically talking about is a sodium channel, but what type of gated channel is it, Sienna? Chemical. I knew you were still one of my favorite former advisees. Good, right? It's a chemically gated channel. In this case, that chemically gated channel is allowing sodium in, right? So sodium comes in, and if I want an action potential to be, or if I want an action potential to occur, I have to depolarize the cell to what charge, Abby? Negative 55, right? Because remember, a depolarization event makes something more positive or less negative, depending on how you want to look at that. So it goes to negative 55. I hit negative 55 millivolts. Lexi, what happens? What do I now open? Huh? No. So I'm still going to move. In this case, I'm still going to move sodium. So I still have sodium moving. So I just went to negative 55. So what type of channel do I open? And you can phone Shayla next. So the channels are in the nodes of Ranvier. All right. So that's in the right ballpark, right? Those are where these channels are being. Okay. Well, so there's sodium specifically, all right, in the nodes. So you're right there. So that's good, right? These channels are in the nodes because again, that's what's happening here as that action potential moves down. All right. Who can help them out? Yes. Voltage gated channels, right, are the channels that Shayla is talking about in the nodes of Ranvier, right, or Ranvier, however you want to pronounce it. All right. So a neurotransmitter, right, opens a chemically gated ion channel. Sodium rushes in. If enough sodium rushes in, we have a depolarization event to negative 55, right? That's the threshold stimulus. Negative 55 opens voltage gated channels. Sodium rushes in throughout the axon, generating our action potential. Okay. Cool. Right, just like the muscle. Guess what? I don't know if we'll do it Wednesday, but at least Friday, at least one more day this week, right, we'll start class like this. So please kind of look over and review exactly what's going on. Now, one of the things, well played, Pointer. There you go. One of the things that I think is important to, yes? Mm-hmm. So is it always going to be depolarization or is it going to be hyperpolarization? So the way that I would say, and this is kind of what I'm getting at here, is that, you know, I guess you could say that hyperpolarization is going to help reset. Here, let's look at it like this. Hyperpolarization is when you're making something more negative if your resting membrane potential is at -70. I think what you're referring to, and I think this is the way I want you to kind of break it down, is repolarization, right? So when you open up some gated channels and ions rush in, right? And let's say you have enough that rush in and they open the voltage gated channels. In order for those voltage gated channels to respond to another stimulus, you need to repolarize, all right? So you need to kind of reset the charge. So, you know, I would be fine if you wanted to refer to the repolarization event as a hyperpolarization. But I think for simplicity, it might be easier to say if you're talking about hyperpolarization, you're talking about making it more negative off of the -70, right? So like going from -70 to -90, that would be hyperpolarization. If I'm talking about resetting the charge for another stimulus to occur, let's call that repolarization, right? That way, that might help you not kind of get them confused. Does that help, Sebastian? And so, you know, again, and this is, you know, where I dinged a couple of you on your exam, not major, right? But, you know, one of the things that I don't want you to forget, right, is you know, we start with that neuron at -70. Okay, well, you know, part of a really good answer would be then why is it at -70, right? And that's because of the pump, that's because of the leak, that's because of the negatively charged ions, right? So kind of keep all that stuff, you know, in mind. And you know, you guys had kind of mentioned potassium. That's why it's like my glasses are off. It made sense why I couldn't see it as well. Like this looks a lot blurrier than I thought it would be. You have your potassium here, right? And potassium is helping repolarize, right? Reset that charge temporarily to prepare that cell for another stimulus. Again, remember one of the things that I pointed out on here is you might look at it and be like, well, if sodium's already in there, why would more sodium want to come in, right? It doesn't show it on this image, but there is we'll say as Thanksgiving approaches, a bountiful amount of sodium still on the outside of that cell waiting to rush in. Just because you had sodium move in here when an action potential started does not mean that when you repolarize by sending potassium out, that sodium is still going to be just as eager to rush back in, right, for another stimulus. Okay. Please, please, please remember here, all right, the idea that the sodium voltage gated channels in the nodes of the nodes of Ranvier or Ranvier, right? This is where they are opening, right? Myelination, right, is an electric insulator, so it allows that signal to perpetuate or move through without having to open these channels. But then that signal, essentially, think of it, starts to run out of gas, right? And so we reopen, right, channels in the node, kind of, we'll say, re-energizes that signal, allows it to move through, right? This is very quick, right? If you would remove these myelinated sheets, you'd have to open segment by segment by segment by segment by segment of those channels, right? So it basically allows you to get more bang for your buck, right? A depolarization event in the node, right, is able to generate enough of a signal to move through this myelinated sheath without having to open any more channels until you get to the next node. Yes, Andy. Ooh, that's a good question. I mean, yeah, I have no idea. My guess would be, you know, there's not like a standard in the sense of they're all 1 centimeter long. I'm sure they have a range that's relatively uniform, but there's certainly, to the best of my knowledge, is not a standard. I've never looked up Schwann cell standard length. It's a interesting. I mean, it's an interesting question. I just have never, you know, gone that deep. All right, you can look that up for me and tell me in lab. All right, cool. All right. So let's talk about synaptic transmission, right? So again, we're releasing neurotransmitters, right, from the axon of one neuron, and then potentially having them interact with channels, right, that are embedded within the membrane of a receiving neuron, right? So in this case, we're focused on chemically gated channels, right? So if a neurotransmitter is opening or closing a channel on an adjacent neuron, it's going to be opening or closing a chemically gated channel. All right. Alterations in these chemically controlled channels results in local potentials, right? So again, if you go back to that original diagram where it showed a depolarization event that I think hit negative 62 millivolts. Someone can go back and check, but I would be willing to bet Haley's life that I'm right on that one. Negative 62 millivolts. Am I right, Haley? On a couple of like slides back, is it negative 62 millivolts for that? Does anyone know? Does anyone have the, am I right?
I was gonna assume you're right.
Oh, well, thank you. It's very generous of you, right? But if you remember, that had like two axons from two different neurons that were opening like two channels, right? And then the picture in the bottom right corner of a neuron on that same slide had a couple, maybe just had one other neuron that was attached to it, right? And was opening those chemically gated channels, and then it got to negative 55, right? So meaning, right, an axon, right, from a, we'll say a ascending neuron, right, or however you want to kind of think about that or phrase that, is interacting with the channels on one part of the neuron. And so it's going to take more than one axon, right, or more than one neuron to cause a depolarization event in a receiving neuron, because it's only going to open channels in that one specific area. And if you're only opening channels in one specific area, you're not going to create a strong enough depolarization event. So you need a bunch of different interaction points that are opening a bunch of different chemically gated channels across that neuron to create or hit that threshold stimulus, right? So that's what we're referring to when it talks about synaptic potentials. We're going to add all of those synaptic potentials up to hopefully get a depolarization event. Or right now, what I'm going to introduce is this idea of adding those synaptic potentials up to actually cause a hyperpolarization. So one of the things that we don't talk about as much, or haven't really referenced here as much, is the fact that you do have chemically gated potassium channels. And so when I open those, potassium rushes out because that's where it wants to go. And when it rushes out, you have a positively charged ion that's leaving, which makes the cell more negative, right? That is a hyperpolarization event. And it turns out, right, that, not that this adds a huge level of complexity, but it does certainly make it a little more complicated, is that you have this neuron right here that's receiving input from other neurons, and it's not just a, we'll say, excitatory or inhibitory effect, right? So what you have, oh, dang it, I guess I have to use my words, right? Is you have something called excitatory postsynaptic potential, EPSP, inhibitory postsynaptic potential, right? So excitatory, right, means that those neurons, right, are opening the chemically gated channels that are allowing sodium to rush in, right? Sodium rushes in, we get a depolarization event, the neuron gets excited, right? We send a signal. Inhibitory, right, releases a neurotransmitter that opens the chemically gated channels that allow potassium to rush out. Potassium rushes out. We have a hyperpolarization event. Depending on the strength of the hyperpolarization event, we don't open those voltage gated channels, and we don't have an action potential, right? And so what we have going on is that some neurons may be releasing an excitatory signal, some neurons may be releasing an inhibitory signal. And it is the balance, right? It's who is stronger. So you could have a neuron that's releasing an inhibitory, but maybe you have 10 other neurons that are releasing an excitatory, right? Well, the 10-to-1 ratio there is still going to allow us to hit that threshold, to hit that negative 55, even though we have some potassium channels that are being opened, right? The reverse is also the same. You could have, right, 5 inhibitory channels maybe that are open, but you have 5 excitatory channels that are then also open, right? And that kind of cancels each other out, and then you get no signal, or you have a slightly stronger inhibitory response, and so you cause, right, a hyperpolarization. Even though you're trying to excite, you can't hit that threshold, and so then you don't send a signal, right? So there's a balance here, right? And there's a high level of control, right, as to whether that threshold stimulus is hit and we open those voltage gated channels. So does that make sense? Right, some of these are inhibitory, some of these are excitatory, right? Inhibitory postsynaptic potential, excitatory postsynaptic potential, all right? Those combined determine if you're hitting your threshold stimulus, which then determines if you're generating your action potential. Okay, does that make sense? Why do you be releasing both at the same time? It's a competition to, I guess, I would say it's a way to, I guess, hold the other in check, right? It's a regulatory mechanism, essentially. Yeah, just to see who generates the stronger response to determine who actually inhibits or who excites. Yeah. Anybody else? It's a really good question, right? It's just a good way to regulate. And, one of the things Sarah would have to look up, and I would assume this is true, is that you might have, some constitutive expression, right? So something that's always happening. And so the only way that you turn that off would be potentially to release that inhibitory signal to stop it. We kind of see, I think I mentioned or may have mentioned before, talk about this in A&P 2, the pacemaker, right, in your heart is actually operates independently of your nervous system. And so it's set at a pulse rate of about 80 beats per minute. And your nervous system then releases excitatory signals or inhibitory signals to help speed it up or slow it down. And so kind of a similar concept here. All right, we're not going to talk about these for too long, right? But we've mentioned some neurotransmitters, so like acetylcholine, right? Norepinephrine are the ones that we've spent a little bit of time on. Acetylcholine the most, right? You have over 30 neurotransmitters that are produced in your body, right? We've already kind of mentioned here that the action potential as it enters the synaptic knob, right? So it's getting to the end of the axon. Increases the permeability to calcium, right? So that means calcium can come in. When calcium comes into that synaptic knob in the axon, that's going to allow fusion of those neurosecretory vesicles that contain the neurotransmitter with the membrane in this knob, right? Once they fuse, they can then release that neurotransmitter. Okay? So again, without calcium present, you aren't able to release your neurotransmitters. Andy? So that would be exocytosis, right? Yeah, so that's what's happening there. That fusion, they merge, right? And then it basically opens up and releases. Yeah, the cell membrane and the synaptic knob. Yes, sir. Yep. Let's see, did I highlight a couple? So these are some important neurotransmitters. So you can see here we've talked about acetylcholine, we've talked about norepinephrine, dopamine, and serotonin, right, are both involved with depression, right? Dopamine, specifically, if you've known someone that has Parkinson's disease, right, their dopamine or their neurons basically become insensitive to dopamine. So one of the Parkinson treatments is to give them extra dopamine. Unfortunately, the body kind of can just keep on upping its resistance to it. I've also heard, excuse me, that like during kind of moments of like pleasure, right? You'll have dopamine released, and this can be a wide gamut, but there's been research studies that have shown like when you go on your Facebook, which I guess maybe you don't use, or your Twitter, or maybe when you get on Insta. Is that what you call it? Instagram? Do you call it Insta? Yeah, I'm so hip, right? But when you go on and like you look for people that like are liking or responding to things that you've posted, right? It kind of makes you feel good. And so, this is one of the reasons that dependency on like smartphones and social media has actually become a pretty big issue, because you're like, or even like with text messages, you're like, oh man, I wonder if that text, is coming back. It's not quite as exciting for me. My text right here is from my mom, which, I mean, I love her, but that's not really, getting my dopamine, pumping. But you know what I mean? And so that's, where we see the release of that neurotransmitter, serotonin. Again, if you have depression, and sometimes more severe depression, we've noticed that levels of serotonin are off. And so antidepressants are going to try to kind of normalize the levels of these that are produced, right? Here, enkephalins and endorphins, these actually help with reducing pain. And so I think I have it on a slide later, but these enkephalins here, they bind to the same receptor that morphine binds to. All right, so this is kind of a natural pain inhibitor. So you see here some of the conditions. Again, we've already mentioned Parkinson's, that are caused by deficiencies neurotransmitters. And so epilepsy, Huntington's disease, which is really, really sad disease that results in death. But here you can see insomnia, right? So inability to sleep, schizophrenia are some of the ones that you've probably heard of. And then here are drugs that can be used to alter neurotransmitters. Notice it has drugs that are illegal on there and are legal, but even the legal ones are going to require prescriptions. And so, some that you may have heard of, Valium, right, for people that are really, really anxious. And so, maybe some of somebody or some of these people that like can't travel or like get on a plane because they just are too anxious and get too worked up. And so you could give them a Valium to help with that. Nicotine, all right, is a huge issue, right? This is what makes cigarettes addictive. And again, the more you smoke, the more nicotine you need to get that effect or that stimulus, because you basically overwork some of those receptors. Cocaine, right? You see here, euphoria. Cocaine actually can be used in certain medical treatments. Interestingly enough, heroin was made from cocaine in an attempt to be used as a medical treatment because they're afraid cocaine was too addictive. Oops, right? So, yikes, right? So you have antidepressants, you have all sorts of things here that are affecting the nervous system. Okay. So let's talk about neuropeptide. I'm not going to necessarily, I'm trying to think, what I would, ask, from here. I might, have a couple of these listed, and then I might throw in a couple of random things there and be able to say, okay, which ones are neurotransmitters, which ones are not. So, I'm not going to ask you to memorize everything about this chart, but I do want you to hopefully, if I say something, if I have a matching question, multiple choice question, you'd be able to identify those as transmitters, right? And again, I'm not going to ask you anything specifically from here, except I do think that it helps you kind of realize some of the different things that, neurotransmitters are doing, or, how we affect, them. Sometimes I think it puts into context, right? If you're like, why do people smoke? Well, people like to be alert and people like pleasure. So cigarettes, right? When people smoke, it makes them feel good. You may know someone that gets stressed, and when they're stressed, they smoke, and it helps take the edge off of that stress. And that's why, right? Because it's affecting those neurotransmitters. All right, so let's talk about neuropeptides really quick. Some neuropeptides are also neurotransmitters, right? So there is crossover, right? So enkephalins and beta endorphins, which I just mentioned on the last slide, as binding to the same receptors as morphine, um, are a group that falls into both categories. And so these neuropeptides are able to also have a modulatory role, right? So they can actually alter the response by blocking or releasing certain neurotransmitters, right? So they can help regulate their release. Small, side note, that is an issue, again, if someone becomes addicted to pain medications like morphine. I think morphine's a little bit harder to become addicted to just by going to the doctor, right? But the same kind of general principle applies for painkillers. And so what happens, right, is these enkephalins and these beta endorphins are produced in response to pain, right? So like I'll use uh, Sebastian as an example, right? Because I've seen him have to hobble along, right, a little bit from like a really intense soccer practice, right? So he has, pain from that, right? But his body produces some of these neurotransmitters in response to that pain. What happens to someone that becomes addicted to painkillers is the challenge in taking them off of those painkillers increases drastically, because those painkillers are occupying those same pain receptors to block pain. Your body actually stops producing these natural painkillers. It stops producing these neurotransmitters because it says, hey, all of their pain receptors are blocked, so we don't need to produce this neurotransmitter. So then you try to pull somebody off of painkillers, right? And some of the side effects that they experience, right? Sometimes they can be really sensitive to pain. And the reason they're really sensitive to pain is because their body, right, is off, right? It's no longer producing these neurotransmitters like it used to, because you were doing its work for them with the pain medication that you were on, all right? So again, substance use is very complicated, right? It's not black and white. This is one of the things that makes it complicated, right? Is it actually alters the expression of these neurotransmitters. And so even if somebody says, I want to get off, or I want to change, or I want to stop, right, there is definitely a physiological component that's working against them that needs to be addressed. And so, I just say that to maybe help you kind of appreciate or understand some of those side effects, all right? I think I'm going to stop here today, and what we're going to start with is impulse processing, this idea of convergence and divergence, right? Basically, showing that neurons that are associated with each other can receive signals more than one neuron. Probably not shocking. They can send signals to more than one neuron also. All right, so this will be where we start. Be looking for my not practice, my extra credit quiz for you guys. And you'll have a regular quiz on Freitag. That's Friday in German. Did you know that? No. Well, see, now you know. I'm giving you the full liberal arts experience.